Alright, well that was exciting. Network issues and lag and getting dropped in calls. Let me see if we can solve this problem though. We have a cop that is sitting alongside the road and there's a speeder that zooms by them. And so the first thing that I wanted you guys to do if you're stuck is to draw a picture and see if we can't. It's 40 and 20, or 40 and 2. So here's your cop. Probably should have drawn this beforehand, but whatever. They're sitting along, and they're on this motorcycle, and the more detail you put, the more confused you are at the beginning, I guess. But when you draw the picture, you actually get a little bit more acquainted with the problem. So we got this cop sitting alongside the road. We know that they're sitting alongside the road, so the velocity to start would be nothing. Their acceleration, we said, was about 2 meters per second every second, so meters per second squared. And there's a speeder, and the speeder is speeding along, and let's draw a speeder real quick. There we go, and the speeder's speeding along at a constant velocity, so I'm going to say v constant, and that's at 40 meters per second. We're going to solve this a couple different ways. We've got some equations to use. If you are absolutely stuck with the physics, you can always go towards the math. So what we know is final velocity is equal to initial velocity plus acceleration times time. And all this says is if you accelerate for a time, you get to a certain speed based on your initial speed. This one says final velocity squared is equal to initial velocity squared plus 2 times a times the change of position. This actually comes from energy, and that's a later topic. And then this one, the change in position in one dimension is equal to the initial velocity in that dimension plus, or times time, plus 1/2 the acceleration times the change in time squared. So this one comes from the graphing aspect. If you graphed it out, the area of that graph is what this equation represents. And so you have the cop, you have the speeder, and we were talking through class, and then we got interrupted by the loss of connection. But hopefully this will get us back on track here. So if I look, I've got 2 objects, and I've got a set of equations here, and I need to use a set of equations for both of these objects separately. And so what I know about the cop is that the initial velocity is 0. And if the initial velocity is 0, then that means that all these v naughts, all these v zeros here, are just 0. And so I have all this information for the cop. So the cop, if I just wrote this down, the cop, we can say the final velocity of the cop is equal to the acceleration of the cop times the change in time of the cop, because all these v zeros are just 0. We can say that the final velocity of the cop, again squared, is equal to the initial velocity, which is nothing, plus 2 times the acceleration of the cop times the change of position of the cop. So we know that. Can't really solve these though. Final velocity is an unknown, time's an unknown. Acceleration we know, it's 2. Final velocity is an unknown. I don't know how far he goes, but the acceleration is 2. So these 2 equations, not extremely helpful right now because I have 1, 2, 3 unknowns and only 2 equations there. And then you got the last equation, which says, position change is equal to the initial velocity of the cop, which is nothing, times time, which is still nothing, plus 1/2 at squared. So the change in position of the cop is equal to 1/2 a delta t squared. So that's another equation that we can use. We don't know the time still. We also don't know how far he goes. And we're kind of stuck still. So the least we can do is we can say, all right, a is 2. And so final velocity is equal to 2 times the change in time. I know that final velocity squared is equal to 2 times the change in time. And we know that the change in position, which we don't know at the moment, is equal to 2, well, 1/2 of 2 times the change in time squared. So if we find the change in time, 2 divided by 2, that's 1. So we'll know how far you go, apparently. And I guess we'll have to see what's going on here. So the speeder also has some amount of information that we know. And the velocity is constant, so that means the acceleration is nothing. Meters per second squared. Really don't even need to write units because it's 0. But a is 0, so that means that all of this drops off. I don't care about anything with a, since it's 0, it all goes away. And so all that says is the final velocity is equal to the initial velocity. Well, that's true because the velocity never changes. If I square those numbers, it's still true because the velocity never changes. So for the speeder, there's only one good equation, and that's that third one there. How far you go is equal to your initial speed, or your always speed, times your time. So for the speeder, we got one good equation. How far you go is equal to your velocity and times the time. And I'm going to have to write some subscripts here if I want to start talking about all of this, because we have some for the cop and some for the speeder. So this is going to be, I'm going to put a car there instead of writing speeder. And then up here, yeah, that kind of works out. So if you are totally stuck, now we've got kind of a guide to help us. And we've got these 3 unique equations up here. We've got this unique equation down here. And we really want to find out how far it went and how long it took. So what I'm going to say is, let's go ahead and look at equations that have how far you are and how long it took. And that's going to be this one, because that's the only one. And for the cop, it's going to be this third one as well. And so the cop goes so far, it's going to take so long, and they're going at a rate of 1/2 AT squared. 1/2 of a is 2, so that's just going to be t squared. So make this look even better. So with the cop starts from rest. Because they started from rest, we can put a 0 in for the initial velocity, and then all you have is 1/2 AT squared to worry about for the cop. Well, the cop goes and the speeder goes the same distance, because remember, the speeder, the moment they pass the cop, that's when the cop started off. Now I know that some of you were saying that the time to catch up would be somewhere around 20 seconds. And that's interesting, because if you say that the time is 20 seconds, well, if the cop is accelerating for 20 seconds, if I put a 20 right in there for the time, that's going to give me 40 as the final velocity of the cop. That is the velocity of the speeder, but will the cop ever catch up to the speeder if the cop only gets to the same speed as the speeder? And if you're chasing somebody, then the answer would be no. You got to go faster than them. And so here with the math, let's just work with math. I know that I go the same distance as the speeder. The cop goes the same distance as the speeder. And so really I can set these two equations equal to each other, because in this problem, the way that we've set it up is, yeah, the cop starts off the moment the speeder passes them. If we want to end the problem when the cop finally catches up to the speeder, then they've traveled the same distance. And they've also traveled for the same amount of time. So I can take these two equations and set them equal. So the change of position is equal to the velocity of the car, which is 40, times however long it takes to catch up. And the change of position is also equal to this for the cop, which only happened to be t squared. And now you can see that the time, if we divide both sides by t, because there's 2 t's over here and 1 t over there, the time is going to be 40 seconds. Okay, that's how long it would take to catch up to the speeder. And because we know that the time is 40 seconds, I can plug that right in there to get how far we went. So 4 times 4 is going to be 16, and we tack some zeros onto that. And so we got 40 to the second power, and we get 1600. So the change in position is going to be 1600 for the cop. And if you're curious, or if you want to double check, the speeder should have the exact same value, and we know that the speeder's velocity is going to be 40, and the time is going to be 40, and so that should work out. 40 times 40, 40 times 40, that should be 1600 as well. So about a mile is how far it takes for the cop to catch up to the speeder. Now, if you wanted to think about this in another way, somebody brought up the aspect of graphing, and if we were to graph it out, we can say that maybe this is a velocity time graph. What we know about the velocity time graph is that for the speeder had a constant velocity the entire time. Okay, so this is the speeder. The cop started off with a 0 velocity, but they were increasing it at a constant rate as time went on. Okay, and so to say that the time was only 20 seconds to catch up, that would mean that they were at the same speed, but they were definitely not at the same position. And another way we can look at this is we can say, all right, remember that the slope of a graph means something, and this slope here is going to be the acceleration. The acceleration, the slope of this blue line should be about 2, depending upon what our scale is, and the slope for the speeder should be nothing. Well, the other thing that we can remember is that area on a graph is also meaningful. And so if we were to look at the area at units here, the area units are meters per second on the vertical and seconds on the horizontal. Okay? And so if we were to take the area is going to be base times height for squares or rectangles, and that's going to be meters per second times seconds. Well, for the area of a triangle, it's going to be base times height divided by 2. And so the area here for the triangle would be how far you went. Well, if we look at the area for the triangle compared to the area of the rectangle for the speeder right now, we can see that the speeder has more area than the cop. But as time goes on, the cop now has reached the speeder speed and is now going faster. And as time goes on, the area for the cop is increasing at this greater rate now. And as soon as the area for the cop is matching the area of the speeder, that's where the speeder gets caught. Okay? And so what we can see, by symmetry here, we can see that it's going to take about double the time that you would think that it would take to catch up to the speeder. So instead of 20 seconds, because of symmetry, looking at the shapes, it would actually take about 40 seconds. Okay? Another thing that you can do is you can take a step back and just say, all right, let's just talk about this conceptually, and let's just talk about the idea of an average velocity, and that's how far you go over how long it takes. Well, we know that for the cop and the speeder, they should go the same distance. They should take the same amount of time to do so. Their average velocity should be about the same by the time they catch up. So if I know that the average velocity should be the same for this problem, then what I can say is, all right, what's the average velocity of the speeder? And the speeder's velocity is always 40. For the cop, though, they need to have the same average velocity as the speeder. They start off at 0. And if you know anything about averages and averaging your grade, if you've got a 0 and you want your average to be 40, then you better make something else to make that average 40 to average out with the 0. And so the answer there would be that the cop's final velocity, the VF for the cop, will have to be, found another ant, 80 meters per second. Okay, in order for the average velocity of the cop to be 40. And so if the final velocity of the cop is 80, and I know the acceleration of the cop is 2 meters per second, then that means that my time, because I'm increasing at a rate of 2 meters per second every second, the time should be 40 seconds. And if the time is 40 seconds, I know that the speeder, the car, is moving at a rate of 40 meters per second constantly, and if the time for the car and cop is the same, then I should know that the distance traveled is about 1,600 meters. Okay, so that's the problem, about 13 minutes, but really it should be a lot faster than that. I'm just going through every aspect, and hopefully we get our internet back soon. All right, bye.